Okay, Ruofan, will you please start?
Okay. Hi, good afternoon, everyone. Today I will present the paper Robustness via curvature regularization and vice versa. This paper is published in CVPR 2019.
Okay, just this one.
The first author is from ETH. The next two authors are from Google DeepMind. The last author is from Swiss Federal Institute of Technology. These four others are well-known researchers in the field of robustness of machine learning. They propose Deepfool.
The other author of Deepfool, the first author is also the first. Is also the first author in Deepfool. Okay.
Yeah, they have many corporations.
Okay. Let me see. What can you briefly introduce this apart from Deepfool? Is there any other very famous work?
Universal adversarial perturbations. I think in this work, they are trying to propose whether there's a universal way to perturb the sample, because usually when we do adversarial attack, it is per sample base. Like for different sample, you add different kind of perturbation.
So it means that given an arbitrary, or will please be more specific on the universal. So
I forget about the details, but
okay.
I roughly remember the idea.
Okay, please go on.
So let me introduce some background first. When we are fitting a classifier, like any kind of classifier, for example, supported vector machine or neural network, it is actually the process of drawing decision boundary between classes. But for the examples that are near the decision boundary, actually they are very vulnerable to adversarial attack, because any small perturbation could flip its label, or flip its prediction. So based on this fact, many adversarial attack methods like Deepfool, FGS, and CWL2 seek to generate adversarial examples by adding a small perturbation while flipping the original prediction.
Please go on.
Defense strategy is called adversarial training. It's where when we train the model, we just generate some adversarial examples ourselves, and then we add them into training or fine-tuning stage. And it can be shown that adversarial training can improve the robustness of classifier. But we want to know what really happens behind adversarial training. We want to have some geometric interpretation, like how the decision boundary and also the classification landscape is reshaped after we do adversarial training.
Okay.
So yeah, this research is focusing on understanding the geometric effect of adversarial training on decision boundary and classification landscape. There are three contributions in this work. The first one is they find that adversarial training decreases the curvature of loss surface with respect to input. And secondly, they prove there is a relation between small curvature and robustness.
They prove through theoretical improvement.
Theoretically prove.
Okay.
And third thing, they propose we can add the regularizer, which directly minimize the curvature in normal training, which can lead to robustness that is on par with adversarial training.
By the way, so maybe I asked a question too soon, but even if with with a boundary with the minimum curvature, is that possible that we still, and how easily can we generate the adversarial sample, or it becomes extremely hard for us to generate the adversarial samples, or it is still possible, or we spend a few times or in computation?
Actually, Actually, it's still possible. And even some simple attack can undermine the model because now my loss surface is flattened, then the gradient approximation becomes more accurate. So
you're right.
Yeah.
You're right. So that means if there's still so many adversary samples, how could they argue it's more robust?
They think that
I mean, how do they evaluate the robustness? So they are arguing that it proposes a regulator.
they evaluate the effort to launch an attack because the attack will add the perturbation onto the original image. So they just measure the norm of that perturbation. If the norm is large, then that means you need to
spend more time to
Yeah.
generate adversary samples.
Yeah.
But it is still so. Maybe I asked the question also too soon. So when they do the experiment, they also whether they can generate the same number of adversary samples for the new models, or it cannot. It only generates much less number, much smaller number of the adversary samples. Let me repeat the questions. Given the new models, whether they will generate the same number of adversary samples, but with longer time, or they generate the adversary sample much less adversary samples.
They will have much less successful adversarial sample.
Okay. Thank you. Keep going.
But they do not evaluate iteratively. They just evaluate once, which means that after you train the adversarially trained model, then you do not continue to attack it, then train again, then attack it, then train again. They do not do this kind of evaluation, but it's also possible to attack again. Yeah.
All right. So that means getting the new model, they do not attack it again. They just using it to see whether the original adversary sample was still successful or not. Okay. Weird. Please go
on. For contribution 1, we need to define how to represent the curvature of a function, right? So we use Hessian matrix to represent the curvature of any function. Suppose we have fx, f is a function here, and x is our input. X is not necessary to be a scalar, it could be a high-dimensional vector. If we take the first derivative, then instead of having a scalar, we will have a vector, because we are taking the partial derivative with each dimension of x. Then we take the second derivative, it will become a matrix.
Yeah, you're right.
So why Hessian is related to curvature? Let's imagine if x is just a single number. Then the Hessian matrix is just the second derivative of f. Then we have learned before that the sign of second derivative is somehow related to the direction. The direction of f is curved. So if the second derivative is positive, then we know that the curve is concave up. If the second derivative is negative, then we know the curve is concave down. Then what about, then after we know the sign means the direction, then what about the magnitude? What if the magnitude of second derivative is large? Because recall that second derivative depicts the rate of changing for first derivative. So if second derivative is large, that means my f prime x is changing a lot. In other words, fx is turning a lot. So it's more curved. Thus, a higher magnitude of second derivative means that the function is more curved.
By the way, do you prepare a few questions in your presentation?
No.
All right, so maybe you can think during your presentations, and I think it is a good point to raise more questions for students to fully grasp the idea. Maybe a few of them are getting the memory is fading for the calculus. But anyway, keep going on.
So the same thing extends to high dimensional case when we look at Hessian matrix. But how do we describe the magnitude of a matrix? We can use eigenvalues. We can use eigenvalues of H, then simply sum them up to get a single number. Then the higher the sum, the larger the curvature.
The absolute value of eigenvector or the sum of eigenvector.
Oh, absolute value of.
Okay. Yeah, please go on. So maybe I ask the questions here. What's the difference? Why we need to use an absolute value of eigenvectors? Maybe I ask these questions. And apart from Ruofan, anyone can answer this question. Xiaoling, would you please have a try?
Can you repeat your question? I'm not.
The question is that given a Hessian matrix, it actually represents the meanings of the curvature, the degree of the curvature. And then we're talking about, and because it is a matrix is very hard as a single measurement. So we want to use one value to represent the overall curvature of the decision boundary, right? So in this case, here the approach proposed using the eigenvalues of the eigenvalues. But anyway, given matrix, they have many eigenvectors. So the idea is that we want to sum them up to be to measure the degree, the magnitude of the curvature. So here we're saying that we should be using the sum of the absolute value of the eigenvectors instead of the sum of eigenvectors. Can you think about why we want to do this?
So if you have a positive eigenvalue and negative eigenvalue, and if you don't use absolute value, then it would be like flat.
Okay, no, you're right. Okay, Ruofan, please go on.
So recall that the contribution one of this work is to visualize the curvature of loss surface with respect to input. So the function f here is actually the loss function. And for a classification model, we use cross entropy as the loss function. Then the curvature profile of loss is the Hessian matrix of loss function with respect to each dimension of input. To show that adversarial training reduces curvature, we visualize the eigenvalues of H for original model, which is in blue, and the model after adversarial training, which is in orange. And then we compute the curvature profile at 100 random testing samples and show the average curvature. For the adversarial trained model, we observed a decrease in curvature because the eigenvalue concentrated around 0.
A question is, how do they apply the adversarial training? Maybe here, let me ask the questions for maybe Darren's or Dorcas. Do you know about what is adversarial training? Is Dorcas there? Yeah, do you know what is adversarial training?
Not really.
Not really. Okay. Selby, do you know about adversarial training? Selby, is Selby there?
Not really as well.
Okay, maybe Ruofan, you can be more specific on what is adversarial training. So in case someone is lost, because not every student have the strong deep learning background. You can just based on that the original slides, you can use the notation there. It will be easy. Okay. Whatever you want. Just explain what is a virtual training. How? Do you want my help?
So, for example, here I mentioned that the points that are near the decision boundary are very vulnerable to adversarial attack. And adversarial attack means I just perturb this sample a little bit. Maybe I reach here.
Yeah, a very famous example is that give me an image of panda, and when we just give a deep learning model, if we train the deep model train on images, the panda will be predicted as panda. However, if we just perturbate or revert a few pixels on these images, the model will predict it as another animal immediately. So from a human point of view, the images is still a panda, but the model makes a wrong prediction. So such a sample is called the adversary samples of the model. So this topic is about the model security. So if the model is so vulnerable, and any attackers just need to crop images with a few pixels to perturbate it and make the model make a wrong prediction. It is very dangerous for the application like autonomous driving, the financial analysis, etc. As long as you want to use deep learning, if the model is so vulnerable, it is quite troublesome. So here, adversarial training is the approach to mitigate such a phenomenon. Okay, Ruofan, please go on.
So adversarial training just like generate some adversarial example, then add this adversarial example into my training example, then jointly train the model. So if we do that, the model can differ in that kind of adversarial samples. Right?
Maybe I can write something, draw something to be more specific. For example, this is so anyway, we know that the classification is random classification boundaries on the space, right? And given the space, we find that suppose this X means it is a cat, and the circle means it is dog, right? So suppose we make a small perturbation, it will be create another X. A small perturbation on high dimensional space, it will create another cat called X prime. And this will causing the model make a wrong prediction. In this case, we will just create a few adversary samples. Maybe we create a few adversary samples here, X or of X. Then we retrain the model. And then if after we retrain the model, the classification boundary will move, will be reshaped a little bit. In this case, the model will be transferable to those adversary samples. So this is the basic idea. Okay, Ruofan, will you please go back?
Yeah, and maybe can I ask a question? So it's the adversary examples will be added into the training data set. So I mean,
it's more like a data augmentation.
Okay. Okay. Thank you.
Okay. So Ruofan, will you go back? Yeah, the adversary. So yeah, these slides. Yeah, my question is that how did they select the adversary sample in this experiment? And do they using the original adversary samples?
They use the adversarial sample generated from the original model to train the adversarial trained model.
I got it. So it means that when we selected the adversary samples and we do the adversary trainings, and we find the original curvatures have been flattened. So that okay. No, keep going.
Can I ask a question? What is the X here? I mean, represent?
Oh, X is the dimension of X because for the Cypher 10 image, you have nearly 3,000 dimensions if you flatten all the pixels. So if X has this kind of dimension, then the number of eigenvalues would be equal to that dimension.
Okay, got it. Thank you.
Okay, keep going on.
Okay.
Oh, sorry, I have one question here, but not in this slides. I'm still thinking about the curvature, the definition of curvature. For example, like fx equals to x squared, then the first derivative should be 2x, and the second, and if you do it twice, it will be 2. Then
Yeah.
intuitively, when x equals to 0, then the curvature should be most flat, right?
You're
That is
right.
the first derivative.
Huh?
It means that at the point of x equals to 0, so both 0, the first derivative is 0, right? But the secondary derivative is 2. Right? So that means at the point of x0, it is very curved. You get that point? So you can think about it. So let me write down here. So small something like this, right? The derivative is here, right? The derivative here is 0, right? Because it's flat. But the secondary derivative is 2. So it means that at this point it's very curved.
But when x equals to any other values, all of them are
always 2.
Yeah, but
so what's the point?
Just intuitively, I think when x equals to 0.
Oh, you got a point. So the curve that looks like this. You think the curvature here is
Should
more
be
curve.
larger.
This is a larger curve, and this is a small curve. Right, this is your point, right?
Never mind.
My point, so maybe my explanation is that at the point of these ones, it has the tendency to keep curving because here the first derivative has a value, has a very large value. So based on these values, it will still have a curve on this direction. But based on I think it's more from a dynamic point. So once you already have a derivative in these directions, and then 2 means that you need to keep improve its changing rate, right?
Then the curvature should be a combination of first derivative and second derivative.
Hey, Ruofan, what's your point?
Yes. So I think it's just a definition. So it may be different from your intuitive understanding.
Yeah, maybe.
Okay.
Yeah. Anyway.
Okay. Yeah, basically it's a measurement. Basically it's a measurement. And basically, intuitively, according to the curvature, if it is very curved, it means that the model is more expressive or overexpressive.
Means the first derivative is changing a lot.
I'm saying that because the measurement, the Hessing matrix, and afterward is a measurement of the curvature, right? Yeah. And the curvature per se is going to describe some property of the model, right? So in this case, I'm thinking about the physical or the semantics of the curvature. Does it mean that the model is somehow overexpressive, or?
Yeah, the lost surface is very expressive.
Okay, keep going.
Alternatively, they directly visualize the loss landscape But because the loss landscape is high dimensional, if it is plotted with respect to x, and x has 3,000 dimensions. So if we want to plot the three-dimensional loss landscape, we need to choose two directions to project the loss surface onto. And the two directions chosen are, the first one is R. R is the normal direction to the decision boundary. For example, this black surface is a decision boundary, then we just choose a direction which is pointing outward. Then V is a random direction. So we can plot the loss surface.
You mean you choose any three directions from the 3,000?
Yeah, you choose two directions, then you can project the loss landscape.
Then how do you choose these two directions?
The first one is a normal direction to the decision boundary. The second one is a random direction.
Okay.
Yeah, but if I'm the one who's doing this, I probably to apply the SVD decomposition and to choosing the most two major directions to do.
Yeah, but here we are particularly interested in the direction which is perpendicular to decision boundary, because that is where the adversarial generated examples lie close to. Then if we do adversarial training, we expect that the loss landscape near this decision boundary will change. So not the rest region. So
basically they can just choose in one direction, right? So the random direction just maybe have the minimum effects. They want to just have a 3D fancy images of like this. So they choose in a random direction. Maybe it's just the first direction.
And then they find that after adversarial training, the loss landscape is flattened. Here, it has two colors. The blue part corresponding to the original classification region of the sample. The red part corresponding to the adversarial region. It is where the sample is classified as other classes.
So this boundary and this shape, can we consider it as the shape of the classification boundary? Do you think it can be considered as such a shape?
Yeah, can be considered, but it's actually the thresholding on loss, not exactly on the classification score, but you can consider it as a decision boundary.
In that case, since I just jumped to the very conclusion you mentioned on the very beginning of these slides. So in this case, if we want to remove the curvature, maybe the dropout is just an approach to mitigate the problem.
Because it reduces overfitting, so you think it's
because it reduces overfitting, because overfitting is somehow means more overexpressive. Overexpressiveness, right? Overexpressive. So in this case, maybe we can add regularizations, maybe L1 or L0 regularizations can still somehow mitigate the adversarial samples, because both approach dropout and the regularizations can minimize those curvature. Oh, but anyway, so giving your first slide, you're saying that the authors also propose another regularizer to mitigate the problem, right? So let's see what they propose. Let's just see what it is their regularizer.
So that one I will introduce in the last contribution. And in addition, they also visualize the decision boundary, because decision boundary is also high dimensional. So we still need to do some projections. Here, they just choose a random normal cross sections of the decision boundary. For example, the black surface is the decision boundary, and you construct a random normal plane that is tangent to the decision boundary, and it will cut the surface with some line, and that line is what they want to plot.
Okay.
Mm.
So they do not reduce the whole boundary into a two-dimensional space. They just find a line and then they project this line to the two-dimensional space.
Mm.
Okay.
Contribution 2 is they provide
And
the
then basically, so when we have the boundary, so so what is okay, so they got it. So I got it. So after they do this, they from the visualized point of view, they find the fine tune is more flattened.
Oh, yeah. So here you see there are multiple black lines, which means these two are different class region, but it's different from the green classification region.
Okay. Okay, please go on.
Contribution 2 is they provide a mathematical proof on the strong relation between small curvature and large robustness. The idea is that they show the lower bound and upper bound of attacking easiness is correlated with curvature. So let us consider a binary classification class where the class is 1 versus -1. For multiple class classification, we can just use consider as 1 versus the rest classification problem. Then if we use the log loss for class 1, so here we consider if the ground truth is class 1, then the loss is just the minus log of probability being x. Then it's easy to see that x is classified as 1.
Maybe I can ask the questions for students. Let me see. Because maybe I can ask Selvi. Selvi, so can you answer why the loss can be negative log px? Is Selvi here?
Yes, I'm here.
Yeah, so
it's because is it because px is definitely px is a probability, right?
yes.
So the log of a probability would be it will be a negative log of a decimal number will be negative, and because you put a negative sign there, it will become positive, right?
And when
Sorry.
if the class is 1 and if px is equal to 1, it means the result of a negative log is 0.
Yeah,
it
right.
means
So
that
there's no loss.
It has no loss. Otherwise, if px is close to 0, it means it's almost close to negative infinity, and the loss will be it will be affinity number. It will be super large, so it will be the value of the loss.
Yeah.
Okay. Okay, keep going on.
So it's easy to see that x is classified as 1 if the loss is less than or equal to log 2, because that is when px is larger than 0.5.
Okay.
So here we use t to represent this threshold. What we are doing is we are expressing the decision boundary in terms of loss threshold.
Okay.
And here, when we do adversarial attack, we add the perturbation R onto the original X. Then by Taylor expansion, the loss of X plus R is approximated by these 3 terms.
So the Rx is supposed to be a matrix, right?
The loss of X is a scalar. The loss.
Oh, all right. So let me see. And what does the T means? The T means transpose.
Transpose.
Yeah. So I'm asking. So I'm asking the derivative of L over X is a matrix.
It's a vector.
It's a vector. Okay.
because this L is a scalar and X is a vector, then the gradient will be a vector, and the second derivative will be a Hessian matrix.
Okay. Okay, keep going on.
Then the process of launching adversarial attack is the following. We have two goals when launching the adversarial attack. The first one is we want to minimize the perturbation added onto X because the perturbation is the attacking effort we need to spend. And the second goal is we want to fool the classifier. In other words, we want the loss after adding the perturbation to be larger than the threshold so that it will be no longer classified as class 1.
Okay.
And the solution for this optimization problem is denoted as R star.
Okay.
And it can be shown that the optimal R star is bounded by 2 bound. Here, C is equal to T minus loss of X. It can be seen as a constant if X is fixed. And J is the first derivative. V is the largest eigenvalue for the Hessian matrix.
But how does these equations is derived?
I can't understand the derivation.
Okay. So, but anyway, so it means that the perturbations have an upper boundary and a lower boundary.
Lower boundary.
Lower boundary. Okay.
Yeah. U is the eigenvector correspond to the largest eigenvalue of Hessian.
Okay. Can I see the previous slide? The previous slide. So it says optimization problems. This one is satisfied. That means if they want to satisfy these conditions and the minimum perturbation R have to satisfy have the upper boundary and lower boundary, right? And why to both have upper boundary? Intuitively. So suppose the R is as large. I mean, I understand intuitively there is a restriction that we want to minimize R, right? But since such a minimization, how this minimization problems leads to a boundary?
They have some derivation. They have some derivation to show, I think.
Okay, so keep going on. I think the first constraint, that means we want to, if we want to change,
this is the constraint. This is the optimization goal.
Well, basically, there's two constraints. Optimization goal is still a constraint, right?
No, you have to have an optimization goal plus the constraint.
I understand. Maybe you can.
But you can interchange the optimization goal and constraint in some way. But anyway, you need to have
any optimization problem can have a due problem. And the due problem is to switch the object and constraints. But so basically, from my point of view, I usually consider an objective is a special kind of the constraints. So my point is that the first constraint. So maybe I'm using the objective and the constraint interchangeably. So the first constraint is going to showing the lower bound. And the second constraint is going to ensure the upper bound. But we don't know the specifics of the the formula derivation, right?
I cannot understand their.
Okay, so keep going. Let's keep the proof. I think for now, especially for paper presentation, there's no need to be too specific on the proof point. Okay, please go on.
Then they plot the lower bound and upper bound. The x-axis is the largest eigenvalue for H, which can be used to represent the curvature of Hessian. And y-axis is the bound for the norm of R star. You can see that R star decreases when curvature increases, which means we need less effort to get adversarial samples. So when curvature increases, the model is less robust to adversarial attack.
Yeah, I think this is very, so from intuitively, it's very easy to understand. But from the proof part, it makes the paper looks more strict. And also it provides the quantitative analysis on how much we can improve the robustness. Okay, keep going on.
Sorry, can I ask an easy question? Why it is less robust shown in this picture?
Because of the y-thesis. The y-thesis is the bound for R star. So it means that because so when it is 0, it means the R star, the value of R star will be very large, right? The larger the R, the more effort we need to conduct a adversarial sample. We need to generate a adversarial sample, and vice versa. So if the curvature is very large, it means that we a single or a very simple perturbation. Simple perturbation means it's a smaller R. We only need a very small R to generate the adversarial sample. Have I explained myself clearly?
Yeah.
The last contribution is they introduce a regularizer on curvature. Because if we do adversarial training, and then it is restricted to the quality of the adversarial samples we generate, and it only flattens some of the local area. But if we use a curvature regularization in normal training, then it can be served as a more general solution. And they find that performance is on par with adversarial training. The regularization they introduce is just the sum of square of eigenvalues of Hessian, and then combine it with the original loss.
About the Hessian matrix is calculated based on some specific samples. Am I right? For a single sample.
Yeah.
Also, they calculate the Hessian matrix for all the samples.
You can do batch by batch, right? When you're training.
I got it. So the basic idea is that for every training samples, it's going to flatten its curvature. Okay. It flattens its curvature on the classification boundary.
On the loss.
On the loss. Okay. I got it. So yeah. Please, Xiaoling, please.
When you calculate the eigenvalues of Hessian matrix, in my understanding, you first need to have a point, then
that's what I asked.
And how do you find the point?
Every point.
Every point.
Yeah. So that's Ruofan explanation.
Oh, okay.
Okay, please go on. Yeah, I think the most that may be the most. So since I want to ask is that whether these regularizations has been compared with the other regularization, for example, the L1, L2 regularizations or dropout technique.
No.
Yeah, I think the CVPR paper does not have strong experiment. So one of my suggestions is that we still using the L1, L2 regularization, because when we reduce the absolute value of weights, we can still have some flattened curvature. Right, but anyway, maybe their effects may be better because they would like to cap the flattened curvature, so every point. And the traditional regularizations may not have such effect. Please go on.
Then they find that the performance is on par with adversarial training.
So the claim adversary attack. What's the approach? The approach is
cure,
called
cure.
cure.
Mm.
Okay, so that means okay. So adversary training achieve better result.
Yeah,
Right.
but for cure, you don't need to add adversarial samples. You just use normal samples and regularize the loss surface.
I think the paper does not have a very good effect, right? So, please go down. And by the way, have you looked into their open review?
No.
Okay, okay. Maybe we like in the future when we look into the AI paper, we also can refer the open review to see how the reviewer makes their comments.
And they find that the eigenvalue profile for cure, which is in green, is similar to adversarial training, just in orange.
But from this plot, it seems the cure is better than adversarial training.
Because you directly add a regular on loss surface, so definitely the loss surface is flattened, but that does not mean your adversarial accuracy will be better.
Maybe the curvature is just one feature into influence the adversary. There's the other facts. Anyway, but they found the correlations. Such correlations may not be the only correlation to decide the adversary samples, to generate the adversary samples. Okay, please go on.
And the paper Xiaolin presented 2 weeks ago focuses on visualizing the decision boundary. And they find that well-trained model has almost flat decision boundary. In this work, not only the decision boundary is flat, but loss landscape is also flat.
But they somehow have a relation between the decision boundary and the loss landscape, right? Okay.
In this work, they visualize loss landscape and decision boundary and empirically observe a relation between robustness and curvature. They also mathematically prove the relation between robustness and curvature. They find that add the curvature regularizer into normal training, the performance is on par with adversarial training.
Okay. Yeah, I think one of my comments is that I would like to, I'm very curious about to see these curvature regularizers to compare with the traditional regularizer in the dropout, because the latter still have the effect of to flatten the classification boundary and the regular and the loss landscape. Okay, so that's all my comments. Is there any questions here? Okay, if not, let's thanks Ruofan and call it a day for today's meeting. Okay, thanks everyone.